Okay. So where did we stop yesterday was this slide. So the difference between batch stochastic and mini batch stochastic gradient descent. And we saw that, okay, yeah, it is here. Actually, let me go to the slide somewhat. Yes. So, yeah. Uh, Yes. So batch stochastic and mini batch stochastic gradient descent. And we told that, I mean, interchangeably, sometimes we use just mini batch gradient descent. I mean, nowadays, I mean, mini batch stochastic gradient descent is so much popular that people sometimes just refer to it as gradient descent or just stochastic gradient descent, but mean this mini batch one. So but yeah, I mean, as I will, at least for the purpose of this lecture, I will try to disambiguate between them by just calling them in these names. So batch, stochastic, and mini batch gradient descent, right? Okay, now let me just quickly tell what is the difference, or what is kind of the additional thing in or not additional, I would say the distinguishing thing in this stochastic gradient descent is that you sample a mini batch m of examples, and sorry, stochastic gradient descent I was telling. So you sample examples xy, that is one sample, and from the training set, and then just compute this gradient on that and apply the update, right? So we have kind of tried to motivate the idea from here that that duplication, or if it, I mean, it's an extreme case. If it contains some duplicated examples, then you are basically saving your computation. So you may think that if you are saving the computation in general, then it must be faster, but it is not always the case. Let me try to explain it in this way. So first of all, this blue path is the gradient descent path, and this red one is the stochastic gradient descent path. Now, what are these circles? So these are the contour plots. So you must have encountered these contour plots in your previous optimization classes, maybe. But if you not, I'm just giving a little brief introduction to it. So contour plots are nothing. I mean, it's in the name, contour plot, etc. Maybe some heavy terms, but it is not. So what's happening is, let me take this horizontal position. So just give me 1 second. Yeah. So this so let us take 2D theta, that is the minimizing argument 2D one, that is a 2D plane, and the third dimension is the basically the loss function plot. So suppose a loss function looks like something like this. It's a 3-dimensional one, so that you can imagine it's a 3-dimensional. I'm just plotting it in this way, and this is sort of the 2D plot, or the axis. Now this is say theta 1 and this is theta 2. So theta, I said, 2-dimensional. So theta has 2 components, okay, and this is the j theta, right? So this is the plot that we are used to see. So what are the contour plots? These are basically you take in the surface, suppose one such line, which is or rather curve, which is on the on this loss function surface, this pole, right? If you project it here, it will be something like of ellipse here. Similarly, if you project this, it is something like this, say this, and this minimum will come somewhere here. So these are the contour plots, and the significance of, I mean, this which when it is projected to this theta 1 theta 2 plane, that is your I mean, that's kind of only shown here, not the j theta, that is the actual 3D plot. So what happens here is that what are these curves? These are the constant value curves. Constant value curves means, or constant value path means, at this every point on this kind of curve, the value of j theta is same, because this is same, right? But the thetas can be very different. So this is say this theta, this is say this theta, this is, or rather I would say this and so on. So this theta 1, theta 2, etc. are different, but these j theta for them are same. So along this curve, the theta 1, theta 2, etc. are different, but the value of the j theta for all those theta 1, theta 2s, or all those thetas rather, are same. So theta 1, theta 2 are just the components, as I said. So theta 1 and theta 2. So this is the significance, or kind of the how does a contour plot is defined. So I'll just stop for a bit. If you have any questions on what is a contour plot and so on, you can please raise your hand, as I said. So raise hand is at the bottom of your screen. So there will be this chat, share screen, etc. And then at the end, bottom right, sort of reactions. So in the inside the reactions, you will get raise hand. Okay. If there is not any questions, let me go ahead. You can also ask the questions in chat, but I am not sure if I will be able to see the chats every time. I will just ask. Yeah. So there is a raise hand, I am saying. So yeah, let me allow you to unmute. So Anupam, I have allowed you to unmute. Yeah.
Yeah, sir, I just wanted to ask, sir, so they are minimizing to the middle circle, right? What is the middle circle represent? Is that the most optimal solution?
Yeah, actually, that's a good question. So the most optimal or the minima is actually a point here inside that circle. So that is one, I mean, this one, if you are asking, that is, you can think somewhere here, very small. I mean, just if you project it, it is somewhere here, right? So the actually mid, okay, let me, clear it and again just draw it. So if this one was the plot, then this middle circle is somewhere here. Okay, so the smallest one. So the minimum one will be just 1 point. So the middle circle is, say, it's like this, and it is the middle. So the solution, ideal solution is this. But the idea is that, okay, if you reach somewhere here, you are fine. I mean, it's so close. Okay. Does it answer your question?
Yes, sir, that does answer my question, sir.
Okay.
And sir, one more question, sir. Is there any like, do we know if like the greedy algorithm in any case works better than like the other algorithms? Like, if like, do we know in case of stochastic gradient descent, is it a greedy algorithm?
Stochastic gradient is not at all a greedy algorithm. So you are intelligently searching it. So greedy was that, I mean, it's not exactly greedy, that was exhaustive search. Greedy algorithm on top of my mind here, I don't know. But if you are telling about the exhaustive search that I started with, that you just randomly sample points and try to find the
Yes, sir.
minima. Yeah. So that's not greedy. Greedy is a little different, right? So greedy is depending based on your previous base, you are just going ahead that thing. So what probably you're telling is the exhaustive search. So yes, of course.
Yes,
I mean, intelligent search is of course more. I mean, better. I mean, this gradient descent, etc. Because you are sure that you are always moving in the direction of the minima.
right direction.
So yeah, so if you go here, the definition of here, so not there. Okay. Next slide. Yeah, this condition is satisfied, right? So whatever your is next theta, so from k-1 to k, when you go, you are making sure that your j theta k is at least as good as j of k theta minus 1, sorry, theta k minus 1, or better. So intelligent search is always better. Okay.
Sir, I have one more question. So in that case of stochastic gradient descent, sir, since we cannot, since it is very erratic, in
Yeah,
nature,
that
right?
I have not come into yet. I mean, I was
Okay.
just explained this contour
Okay.
plot, why this is an
Okay,
outcome.
sir. Okay, sir.
Yeah. Okay. Yeah, I think I am seeing a raise hand of Rishabh. I'll take this question and then I'll move ahead. So I have asked you to unmute, Rishabh. Oh, raised hand. Sorry, lowered your hand. Okay, so let us go ahead. Let's see. Okay, so yeah, I think let us take this from what Anupam was asking last, that it is erratic. So why it is erratic? I was just trying to explain. Because they see, first of all, yeah, so I explained the contour plot. I said that this blue one is corresponding to the gradient descent, and this is the stochastic gradient descent, the red one. So what does these arrows mean? So this was, say, one theta, then the next theta, then the next theta, and so on. But remember that going from here to here, you are actually computing the gradient on all the examples for gradient descent. And going from here to here, one theta to next theta in stochastic gradient descent, you are computing the loss for only one example, right? So that is a little, I mean, that you should keep in mind, that though it is one step, the one step here and one step here means less, I mean, different computation. Now, since you are computing only okay, well, let us first talk about the blue one. So since you are computing the gradients for all the examples in gradient descent, if there are any noisy examples, so by noisy example, I think I can give one example, one scenario, maybe the regression scenario. Suppose you are trying to find what is the say line here. So you are asking, I mean, you are told that it's a straight line. So you can try to fit a straight line, something like this. So these are the data. So these are y's and these are the x's, right? So you want to find the y is equal to fx, right? Or f hat x rather. If x was a true one and f hat x is the predicted one. Now, suppose one data is so noisy that it is here. So when you are computing the gradient for, say, this one or this one or this one, they are more or less going to the right direction. I mean, they are forcing the gradient theta to go into the right direction. But this one will erratically actually go into some other direction. Now, when you are doing gradient descent, these things will average out. These if there is some noise, when you are averaging the gradients, these things will average out. So it will always move towards, it is expected to move towards the right direction. But in case of stochastic gradient, because you are relying only on one example, when suppose at this point, maybe this data came, so it will be a towards some other direction. So that's why this sort of erraticness you will see, but ultimately it will go. So that is sometimes a problem, and that's why it is slow. But again, slow means in number of updates, not in number of computations, right? So before I go to the next slide, which will bring me to momentum, I see a raised hand still from Rishabh. So let me ask him to unmute. Is there any question?
Yes, sir. Sir, can you make the previous slide 41? Yes, sir. So, in this, sir, you said that we won't directly convert to a single point. We just convert to a smaller curve, circle in this contour.
Oh, the minima, you are saying.
So the point is, like in this circle, we will be having like infinite many values of theta. So how do we choose? Because we don't have one single value, sir.
Yeah. So what I meant by this is that, suppose, I mean, you would ideally want this one to be your solution, the center one. But sometimes what happens is that the gradient signal, when you reach, I mean, when you, so if I go to the single scalar example case, so the gradient value, okay. Yeah, I mean, I wanted to draw it here. So the gradient value here is high, then gradient value here is low, then here is pretty low, right? So when you are moving, so you will be moving very slow. So many steps will take to actually exactly reach here. So what I mean by this, when I told this statement, is that if you are reaching, this is sort of the tolerance circle. So if you are inside anywhere here, your practical purpose will be served. So for what you are learning the model, maybe that prediction model is already doing good. So that's what I mean, that sometimes it is okay to just be in any of the points. If you just reach any of these points, you may stop. Okay.
Yes, sir.
Anupam, I see a raised hand again. Do you have any other question? I will ask you to unmute.
Sir, yes, sir. So actually, I was trying to ask this question earlier, sir. So in the case of gradient descent, you said that they average out, like even if there are noisy points, they
Yeah,
average
mostly
out.
they average out.
Sir, but how can you guarantee convergence with stochastic gradient descent then? Like, what if it keeps choosing noisy points at random?
Yeah, if there are always noisy points, say you have 10,000 training data and you have 9,900 noisy, then of course it will be a bad model. I mean,
No, sir, I mean,
no algorithm will converge there, right?
sir, I mean, like, because we are choosing random points at every iteration, right? So then, sir, my question was, sir, how can, like, how is it known that stochastic gradient descent will converge always?
See,
Like, can we guarantee?
yeah, there are, yes, there in the paper that we told you, just go there. There will be some, there is some theory of that. I mean, there are lots of, I mean, books even on that. Yeah, but the thing is that what I'm trying to tell is, if always it chooses random point, that means what? The chance of choosing random points is high, right?
Yes, sir.
So when will be the chance of choosing random points high? When the number of random points are
Higher.
noisy, not random, the noisy points are high. So that means in your training data, most are noisy. So in that case, no algorithm will convert. Okay.
Okay, sir.
Yeah.
Okay. But we know for certain that it converges.
Yes,
like
yes. I mean, of course, there are some conditions. Of course, there are some conditions of these noisy labels and so on. So that I'm not again going into that. That for all our practical purposes, that doesn't matter, actually, right?
Okay, sir. Okay, sir. Thank you, sir.
Yeah. Okay. I will not take science question at this moment. Let me move ahead a little bit because we are going slow, and then later I will ask. Okay. Okay, now suppose the loss function is, so Anupam, if you are done, you can basically lower your hand. Okay, so suppose loss function is steep vertically and shallow horizontally. So what does it mean is that you have a very elongated surface. I mean, this kind of contour will happen if you have a loss function like plot like, I mean, okay. This, I will erase it. So very elongated one, then only you will have this kind of a contour plot. So what happens is that basically in one direction. So if these are the two, theta1 and theta2, say this is theta1 and say this direction is theta2. In one direction, the loss function decreases a lot, and in another direction, the loss function decreases very less. So this is the direction where the loss function, I mean, if you change theta a small bit, the direction, the amount of change in the cost function is very less. But if you change, I mean, in this direction, it is more, basically the other direction. So why is that? Let us try to see first, and then I will come to it. So this is some value, a loss function value, which is constant throughout this circle. This is another one. And as you have seen, for a convex bowl type of a functionality, the inner ones have lower basically values, right? Inner ones have just give me 1 second. Yeah, inner ones have lower j theta values, right? The loss function, so the inner circles. So now, as you move a little bit in this direction, actually, or let me just tell it in another term. To go from one level of cost function to another level, I mean, just let's say that this cost function is 10 and this cost function is 9. or maybe it can be even 8.5, whatever. So wherever have we drawn this contour, so going from one level to the another in this direction takes you a lot of path. So what is the definition of gradient? Change divided by change. So the change of loss function to go in this direction, right? So that is a partial derivatives definition. So this is actually small, the change is small, so that way it is this component is small. But in this direction actually it is the I mean for going from same level to same level, say from here to here, so I mean you have to move less, so basically the denominator is less, so this gradient is high. I mean in theta, I think I said theta 2 this and theta 1 is this, right? Now, so that's why in such, this is called a not so well behaved loss function. So this is where those condition numbers in linear algebra, those concepts come. But the geometric intuition is this: it's an elongated surface in one direction and non-elongated in another, right? Or narrow in another. So now one thing is that if you I mean actually the gradient is in this direction and this direction, so these are actually the negative of the gradients, because you see in case of scalar it is easier to basically explain. The gradient at this point is on actually upwards, but what you are moving actually in this direction. So this red basically arrow is actually what I am trying to think as the direction of movement, not the direction of the gradient, just that, but it is just the negative of the gradient component. So this is the partial derivative with respect to theta 2, and this is the partial derivative with partial derivative of loss function with respect to theta 1. And you know that partial derivative of, or rather the gradient of j theta, it has two components. Actually one is del j theta del theta 1, another is del j theta del theta 2, right? So these are the two components. Now if you try to, what is the trajectory along which we converge towards the minimum with this SGD? So if we try to converge here or try to apply our SGD algorithm, what we would have wanted, I mean this smiley face is where the minimum is, so we would have probably liked to go directly there, something like this. But what we will do is we will move as a let me actually clear all these markings. We will move to a resultant of these two. So these are the two partial derivatives. So actually this is the direction we will move somewhere here. Then here if you compute again, so it will be in this direction something like this, in this direction something like this, so we will move somewhere here and so on. It will be jittery. So we are not going to that going via the, say, the ideal path. Ideal path will be of course the straight line, but yeah, something similar in between would have also worked, right? Now, so this is the jittery plot that I was showing, that very slow progress along flat direction and jitter along the steep one. So in this direction, the elongated part, it will be very slow. I mean, if you just think that, okay, in one, sorry, yeah, so yeah, so in one direction, let's just not confuse us about what is flat and what is steep. So in one direction it will be slow, and in one direction it will be very fast, right? So it will be jittery. So that's the thing, and we are not going to get this. So let us try to see how can we get this sort of a near ideal path of convergence. So what I'm now let us dissect this path a little bit more. So when, let us just think these 2 points, that is this red and green points. So when the red, I mean theta is here, and when the theta is here, suppose this is like theta 1 and theta 2, this is theta, oh no, again not theta 1, so say this is theta k, and say that is theta k plus 1. So when theta k is moving to theta k plus 1, it is moving under this resultant gradient, right? Let me clear up the markings. So actually this okay, again, this one. But when you are computing the gradient for the green one, it is sort of completely forgetting what brought it here, right? It does not have any effect of the gradient that brought this green point from this red one. Again, a new gradient is computed. I mean, it's a fresh gradient that is computed. But if we can actually try to remember the direction that it was traveling before you compute this gradient, that can help. Because if you take now some sort of a resultant, or yes, I mean, yes, the sum of these two with some weighing, of course, that weighing I will come. But if you are maybe taking this some sort of a resultant of this, it will be somewhere like this. Why? Because of course the force of the gradient is more in this direction than in this direction, right? Because at least some loss has been decreased going from red to green. So it is at least not going very jittery in this direction, that is in this direction. It has some corrections, but we would have liked somewhere like this. So how to get this, I'll come. But let me just try to tell what I was basically telling and complete this. So let us see. So yeah, just give me 1 second. So this is basically, yeah, I was going to tell that the gradient isn't only one. I mean, what I told last slide, only one force acting at one point, right? Now, suppose that if we think now, I mean, I am trying to defer the physics analogy, but let's try to come here. So this is actually, we are trying to go to the momentum based methods. Now, it is completely fine if you don't think of momentum even, because when I will come probably in 1 slide or 2 slides, the actual algorithm, you will see it's just a small change. And what I said, the crux of the matter is that you need to take a resultant, some sort of a resultant. Why I'm not telling full resultant? Because it's not just the sum of these two. It is a weighted sum of these two. It will do the job. So if you don't even remember the analogy of momentum, the physics analogy, it is completely fine. Let's see. But still, just because it's a legacy and for historic reasons, I mean, these were called momentum-based methods, etc. Let us try to at least mention about this analogy. So if we think of physics analogy, then we consider this point, these thetas, this red, green, etc., which are just different values of thetas, right? Just to remind you, say these are just the two axes of theta. I mean, I think I denoted this as theta 1 and this as theta 2, just for 2-dimensional case, but it is equally true for high dimensional cases also. So if we consider this as a particle moving along this surface, so I mean, I'm again just drawing a smaller version of this. So if you just think about this, that you are moving along this surface and you want to reach here, and the corresponding theta you actually would be declaring it as the minimizing argument. So if you take that analogy, then you can think that this particle is moving under some forces, right? And there are two players of the forces. That is the momentum built up due to the gradients pushing the particle at that point. So this one force. So this again, I'd like to clear that. So this is one force, and then again some new force is coming as the red arrow, right? So gradient computed at that point. So if you now think about this, then or think about this analogy, then the momentum-based method tells that, okay, what you are doing in stochastic gradient descent is that you are not considering momentum. You are what you have built up, what have put you here. You are just considering the force that is instantaneously applied. Rather, if you consider both of them, then actually you can basically move in towards the direction of the minima quickly. So for that, let us now go to the algorithm. This is just the analogy. I'll just not tell about, I mean, I would rather refrain from going to this analogy not more than in this slide. So let us go to the algorithm. It is very simple, just a small change to the actual stochastic gradient descent. So now I think this part I told earlier, that though it is stochastic gradient descent, it is told in the book. I mean, this is taken from the book, Goodfellow's book, and chapter 8, and I mean, it is told it is a stochastic gradient descent, but you see, you are sampling a mini batch. So this is that interchangeably you can use the same term. That's what I was telling. But what it basically means is the mini batch gradient descent. So you are just introducing one parameter which is called velocity. It is just the name velocity. You just see what it is. You will see. So what you are doing, you are sampling m examples. Now you compute the gradient, that is the loss, and then compute I mean, sum it or average it rather, and compute the gradient, right? Or I mean, the opposite thing is also true. You can compute the gradient and then average, because it's a linear operation, right? Gradient and sum, so you can interchange. Now initially what you were doing, this g, what you were computing, you were adding to theta as negative. So theta was theta minus epsilon into g. Instead, this line is added here. What is it telling? It is telling that your new v is your previous v minus g, and it is suitably weighted. So this epsilon was the step size parameter. You are just adding that here, and this is the alpha. So you are multiplying this v with this alpha, and the step size parameter with the this your new computed gradient with epsilon, and then you are adding. So that's the actual step, that is this v, and then you are changing the theta according to this v. Now you see, previously it was minus epsilon g, and here it is plus v, because already this minus epsilon g is taken care of here. So this thing is computed. So this is basically your minus epsilon. Yeah, as I said, in that loss landscape, these are all the negative gradients, right? So actually the gradient is something like this. So this is actually negative gradient. So that's why this epsilon, negative epsilon g, and this you are multiplying with alpha. Now what are the values of alpha? Alpha is actually it is chosen between any value between 0 and 1, and typically the values are 0.8 to 0.9. Why? You see that if alpha is larger than epsilon, the current update is more affected by the previous gradient. So you see this is where alpha is coming. So if alpha is more, then your resultant will be more towards this, right? So if alpha is, say, very less, then it will be more towards, as it is less and less, it will come this, I mean, this actual step or the resultant, this p will come this. Just one thing, I think I forgot to mention, or is it not here? I think v is actually initialized with 0. The text of the book actually tells. So initially it is just your epsilon g, right? So this is the momentum analogy. Yeah, let me just do this slide, and then I'll stop for questions. So nested of momentum. Nested of momentum, I will not go into detail. I mean, it is just where do you compute your gradient. So the difference between nested of momentum and standard momentum, the one that I told earlier, is where the gradient is evaluated. With nested of momentum, the gradient is evaluated after the current velocity is applied. What does it mean? So in all the algorithms where actually it is important, or where actually the change is happening, that is given within these red boxes. So you are sampling the examples, the mini batch, then apply the interim update, that is whatever momentum, again that v, I mean, though it is called momentum based method, this v is called velocity. So you apply that. So theta, you move there. Whatever is your previous gradient, you move one step more. So you kind of looking ahead, you are predicting where it would have gone if there was no other instantaneous force, just the momentum was there, and there you compute the gradient. So at that theta, you compute the gradient, and you again then just the same thing. I mean, you do this resultant of the momentum and the gradient. So again, I mean, there are many details. I mean, Nesterov is one of the stalwarts in optimization. He has many methods, so you can actually, I mean, there are books written by him on this. So I mean, we cannot probably summarize these things in one slide, but just for your information, this is given, that this is just the difference between simple momentum and Nesterov momentum. So Nesterov's idea can be employed in other optimization based methods, and we will see in the last algorithm that we'll discuss, the Adam algorithm. We will see in practice, Nesterov momentum speeds up the convergence only for well-behaved loss functions. So only for the bolts which are not elongated, very much elongated in one direction or flat in one direction. So convex with consistent curvature. So that is what people have observed. So I will stop here for some questions, but yeah, we have quite some more things to cover. So please keep your questions brief at this point. If you have any questions, please raise your hand. Yeah, I see Rishabh has raised his hand. I am asking him to unmute. Yes.
Just one small doubt, sir. Like in previous case, when we are using SGD with momentum, sir, it doesn't remain stochastic, sir, because sir, stochastic means randomly, and it doesn't remain random now, because sir, we are also accounting the previous step. So it's similar to what we are doing in SGD, sir.
No. Yeah. So there are two basically things that I want to mention here. One thing is that when you say that stochastic moves randomly, it's actually randomly, it samples the image. I mean, it is not that theta moves randomly. It randomly samples the examples from the n set of training examples. Suppose you have a set of n training examples. From that, you choose one. But what I am telling here, so you just don't think that theta moves randomly. The example that you are taking, to the training example that you are taking to compute the gradient, that is chosen, that is sampled randomly, nothing else. Another thing is that what again I told is that though it is called stochastic gradient descent, it is actually the mini batch gradient descent. So what is mini batch gradient descent? It is in between batch and stochastic, right? So you are actually sampling not one single, and not you are not also computing the gradients on all the n examples, but some m examples which is less than n, but more than one. So that's why it is though it is told stochastic gradient descent. I said that it is so popular that when people say stochastic gradient descent, sometimes they mean the mini batch gradient descent. So I said that, I mean, you have to look into whether you are summing or averaging, and how many examples you are summing or averaging it, which is I mean m, which is less than the total number of training examples, or n, which is all the examples, or you are not at all averaging, just taking one. So that way you need to figure it out, right?
Yes, sir.
Okay. Any other questions from anybody? Okay, if not, let me actually go ahead with okay, this is one thing that you can actually look into it. This is now it is a little old article, but yeah, I mean, you can visualize. I mean, there are two parameters in this momentum based methods, right? These alpha, or not parameters, the hyperparameters, or rather you can say design variables. So this is alpha and epsilon. So alpha is the momentum parameter here, and learning rate or step size is the epsilon. So this article, this is a distill.pub article. So distill is a OpenAI started blog. I think they have probably discontinued now, and it tries to publish blogs which are publication quality, and people actually have cited their blogs in papers also. So if you can actually slide these, I mean, this is a well-written blog. You try to see why momentum really works, their idea behind it. And this step size, that is this epsilon, and what we called as V is this beta. So if you change them, how for the same loss function, the convergence path is changing, that you can also see, visualize. So I would encourage you to look into this. Now we are going into another philosophy or another school of thought, which is adaptive learning method. So what does it tell? That okay, till now we assign the same learning rate in all directions. So the epsilon we are using, so even if it is theta1 or theta2, or rather let us say g of theta1, g of theta2. What is g of theta1 and g of theta2? This is the partial derivative of j theta with respect to theta1, and this is the partial derivative of j theta with respect to theta2. So we are seeing that theta nu theta is your old theta minus epsilon into g, right? Or it's like theta plus alpha v minus epsilon. But the important point to note is that this epsilon applies equally well to all the partial derivatives, because this is a scalar, right? So when you multiply this scalar with this vector, it is equally getting applied to here. But we know that the magnitude of one of these component is high and another component is low. So a naive solution, we can think that would it not be a good idea if we can move slowly in the steeper direction? That is where the gradient is high. If it is steep, the loss function, the gradient will be high, right? So whereas move fast in the shallower direction, that is this one. So if in this direction we can move slow, and in this direction move, or rather the opposite. In this direction we can move fast, and in this direction rather not move fast, so that the jittering will be less. So that is a very naive idea, and that's actually give rise to this adaptive learning rate. What is adaptive about it? That you adapt it according to the gradient component or magnitude of the gradient component. So let us see. So what it says is very simple. Downscale the learning rate by square root sum of squares. I mean, not say focus much on by what amount it is downscale, but downscale. Okay, downscale on basically the direction where your gradients are always high, some sort of that. Let us see. I'll come to the algorithm and an explanation in the next slide. That will make things much better. So parameters that have large partial derivative of the loss, learning rates for them are rapidly declining. So that is the thing that achieves this. Okay, let us see. Again, only changes are in these red boxes. So you have this, this delta is just, I mean, I'll come to that. I mean, it's not that important. I'll come. You introduce one more hyperparameter or a design variable, so to say. In machine learning terms, they are called hyperparameters. That is initialized with 0. That is called R. And remember that R is a vector and 0 is also a vector. So all components of R is basically initialized with 0. So now you take this, that sample xy from the training set, then this is compute the gradient estimate. Now you accumulate this gradient. Now what does this notation mean? This dot within circle, it actually in the context of this lecture means element wise multiplication. So you basically try to multiply each element. If it is d-dimensional theta, that is if theta has theta 1, theta 2 to theta d, of course your g will also be d-dimensional, right? So g1, g2 to say gd. Then you multiply or basically take square of these things element wise, right? You don't do like inner product or anything. So that's what you will do, and then you will basically divide it by the square root of all these individual terms. It may not be clear at this slide. Let us go to the next slide with an example. We will try to see. Suppose, as I said, theta is a d-dimensional vector. So then g hat 1. So what is g hat? G hat is the computed gradient. And what does this 1, 2, etc. mean? This basically means the step. So basically, so here, this while loop you see. So you are sampling one example from the training set. So this is pure, this is adaptive learning rate applied to pure stochastic gradient descent, not the mini batch. So that's what at least this algorithm tells. So you take one example, the first one, that gives you G1. You take the next one sample, that gives you G2, and so on, right? That is basically the iteration number in this while loop. This 1 and 2, this T. So T means T samples have been taken. So you are computing them, and I am just denoting these D components as 1, 2 to D, and this within bracket is the step number, you can see, iteration step number, right? This I hope it is clear. Okay, now what you do with the next line, which is R. Okay, yeah. Oh. So R is previous R plus the element. I mean, you add the element wise squared values of G. So what does it mean? First, you need to square. So I think what you are doing is, when you element wise multiply this vector with the same vector, see that it is the same vector G hat with G hat, right? But element wise multiplication. So this is G1 squared, G2 squared, G1D square, right? So when you are adding it with R, after you do this squaring, you are adding it with R. So you are adding it with R, but remember R is initialized with 0. So what is your R1, the R value after step 1, or rather, yes, the iteration step 1, it is just the squared values, element wise squared values of this G1. What is R2? Previous R, that is this plus this element wise addition. So G11 square plus G21 square, G12 square plus G22 square, right? So what is similarly RT? All the previous or all the basically historical gradient values or partial derivative values along this component, they get added, the squared ones, of course. Now, what does this line tell is that you basically do this is your delta theta. That is the change that you will add to get the new theta. It was previously just epsilon into G, right? Or G hat rather. Now it is telling that you do this. You not only epsilon into this component, you divide it by this magnitude for GT1. So that, I mean, the square root of this magnitude. So you are taking this. For the next component, you are dividing it by the square root of this. Now, if your historically this component has higher magnitude, it will move less, because this is your delta theta. So this component will be less compared to, say, this, where this denominator is lower compared to. So if this is lower, this is high, and if this is and if this is actually higher, this will be low, right? And what does this delta? Delta just avoids division by 0. So it's a very small value, just so that if somehow these values happen to be 0, I mean so small, then it will get divided by, I mean this thing will get divided by 0. So just to avoid that, a very small value is given. Now, let us actually go ahead with the small variation of it, and then I'll stop for the question. So RMS prop is just one variation of it. So why does this variation is required? Why is this variation required? Is that one problem? Oh, okay. This algorithm is called ADAGRAD. So adaptive gradient based methods, right? So So one problem of ADAGRAD, that is the previous method, is that R vector continues to build up and grow its value. So see, at tth instant, it is always the square of the 1th instance value, then the second 2th instance value, second instance value, third, and so on. And all are squares. So after, say, 1000 iterations, it will just have add 1000 positive values, right? So it may actually stall the progress, because you are dividing with a very high value after, say, 1000 iterations. So it is so small that it will not, the thetas will not move. So that's a problem. So how can you basically get rid of this problem? You don't add all of them. Maybe take very recent ones, and you can discard the distant past. You can give more weightage to the recent ones, give less weightage to the distant past, and so on. So the second variation that I told, that you give more weightage to the recent past and less weightage to the distant past, that is called the RMS prop. And the first one, that is you actually discard maybe the distant past and take only say n minus say m, or not nm, say just giving some ballpark value, say 5, last 5. You take last 5, you discard everything else. So that will be ADA delta. So this is RMS prop and that is ADA delta. Now this RMS prop actually cleverly does this. So RMS prop strikes a balance by exponentially decaying contributions from past gradients. So as you move ahead in your while loop in this iteration, exponentially the previous ones will decrease. So what that means is that only one change, there is one more hyperparameter that is introduced, that is rho. It is now, it was previously r was your r plus g hat, and g hat this element wise multiplication, right? Now it is rho times r, so you are multiplying or weighing this r with rho and weighing this with 1 minus rho, and rho is any value between 0 and 1, right? So let us see what will happen in this case. So as we said, I mean, g1 hat, g2 hat, these are the gradient vectors for different time instants or iteration steps, t1, 1, 2 to t, and your rt is this, right? So r0 is 0 because that is what you initialize. What is r1? It is rho r0 1 minus rho into g hat 1 element wise multiplied with g hat 1. So since r0 is 0, this is just this term is remaining. What is r2? If you just put it in this formula, rho r1 1 minus rho into g hat 2 into g hat 2. I mean, by into I mean element wise multiplication. Now if you put r1's value from here, it is this and this. Similarly r3. Now if you see r3's value, in r3 the g1 component, the square of the first iteration steps values, they are multiplied with rho square, right? So in r4 it will be multiplied with rho cube and so on, but rho is between a value between 0 and 1. So actually it will decrease, right? So that is and if it is yeah, so it will exponentially, as your t value or the while loops iteration step value increases, this will basically get less and less weight. So so that's why it is called exponentially decaying average. It is probably not immediately clear from the algorithm statement that, okay, how is it exponentially decaying? So if you just expand it, it is becoming clear. ADA delta is another, as I said, where instead of in exponentially decaying average, a moving window average of the past gradient is taken. That means you discard all the previous ones, just keep a fixed length of window, say 5. You take only the recent 5, last 5. Then this thing I said that nested of acceleration can also be applied. So nested of acceleration does not have anything to do with this, right? You can nested of acceleration just say that you compute it in a predicted position. Whatever your previous gradient was, you just apply it before compute the new gradient, and then do everything on that new position. So look ahead position. Now I will stop for a bit, but I have one more topic to cover. So maybe I'll take 4 or 5 minutes of Adam. And the next topic that I will cover, it just combines everything. So we have 2 schools of thought mainly. The momentum, which this next topic, which is called Adam. Adam actually tells momentum as the first order moment. Momentum is what? You just combine your previous gradient and new gradient to give your resultant gradient. And what is this adaptive learning rate methods? It says that, okay, if I am moving fast in one direction, I will just slow its progress, and the vice versa. This is, in Adam term, it is called second order moment. So we will see that they just apply these two, and one more additional term that is very intuitive, and it keeps you the Adam method. So, but if you have any questions on these adaptive learning based methods, please raise your hand. Okay, I hope there is not a question at this moment, but yeah, let us go ahead with Adam. So yeah, as I said, variant of the combination of RMS prop and momentum. So what by this, what I mean is that those momentum based philosophy and RMS prop, that is the adaptive learning rate based philosophy. So incorporates first order moment of the gradient, which can be thought of as equivalent to taking advantage of the momentum strategy. So whatever this paper tells, Adam paper or Adam method tells as first order moment, it is basically the momentum strategy. Here momentum is also added with exponential averaging. So the exponential averaging that RMS prop comes up with, you are adding both this because there is no conflict in these two, right? The momentum strategy and this adaptive learning. So you can very well combine. It also incorporates the second order term, which can be thought of as RMS prop like exponential averaging of the first variance. That's what I told a minute ago, right? Now, both first and second moments are corrected for bias to account for their initialization to 0. What does this bias mean? I'll basically now explain. It is, let's say, let us explain in terms of the RMS prop analogy, right? Or RMS prop scenario. So you see that this rho value, it is between 0 and 1. Now, generally, this rho value, or if the rho value is taken pretty small, suppose say 0.1, right? High, so 0.9. So you are actually taking this rho as say a high value. I mean, you can take any value between 0 and 1. Then what you are doing is that since R0 is initialized with 0, this R1, it is kind of dictated by this R0. Because why? Because what is R1? It is 0.9 times R0 and then 0.1 times this G1 hat multiplied with G1 hat and so on, right? Now, this is, even if your G is actually high for say every direction, if it is high, it is actually stalling the progress because it's maybe a well-behaved loss function, and actually you are very high on the loss surface, so you need to move quickly on every direction. But since your R0 is high and rho is also high, you are actually not moving as fast as you expected because this term is dominating. This is making it 0, and only 0.1 part of what your gradient signal tells you to move, you are moving. So that is kind of sort of meant by telling that it is biased towards the initial value of rho, right? Yeah, Anupam, I have seen your raised hand. I'll come to that. Now, what is R2? So R2 is now same. So this 0.9 times R1, and this suppose is a high value, it is not going to exploit that because R2 is then biased towards R1, and R1 in turn is biased towards R0, which is 0. So this is the idea behind the bias. So okay. So both first and second moments are corrected for bias to account for the initializing to 0. So I'm not going into the detail for the first moment, but you see that first moment is also, it was previously told as, if I remember, alpha into V plus epsilon into, or minus rather, minus epsilon into G. So if this alpha value is high, then you are basically biased towards this V value, and V you initialize with 0. So same thing happens in the momentum strategy. So let us again combine, but before combining, again just quickly summarizing, Adam combines both, that is first order moment and second order moment. First order moment is just the momentum strategy, where you find your direction to move by resulting by finding the resultant of your previous gradient and new gradient. And your second order term is the adaptive learning strategy, where you move less according to the magnitude of the partial derivative. If it is high, then you move less, and if it is low, you move more. And then this bias correction. So this is what the crux of the Adam algorithm is. I mean, the whole algorithm form is given in the next slide, but I'll not go into like detailed explanation of that algorithm. Rather, I'll spend time here. So what is the biased first order moment? It is the momentum term, right? So they are just telling it as S, that V. So I have not changed these notations. I mean, these are taken from both the paper and the book, and I just kept the same notations, so that if you need to say move into the paper sometime, maybe 3 months later, things are not confusing. So ST is rho 1 times ST minus 1, that is the previous velocity, and 1 minus rho times the new gradient. Now, we earlier saw that this was alpha and this epsilon, but you can very well take this alpha plus epsilon is equal to 1. And that's what they are just taking. And this value is just they are taking rho 1, because the other value which we used as rho for the adaptive learning based method, RMS prep, that is taken as rho 2. So bias second order moment. Why biased? I have explained, right? I mean, I have not done anything to bias correction. I mean, to do the bias correction, it is very easy. I mean, if it is rho, you just divide it by 1 minus rho. That's what we are doing. So if I just keep this at for the moment, bias corrected first order moment is this. And what is the bias second order moment? That is basically the adaptive learning rate state. So it is just rho times R plus 1 minus rho times GT element wise multiplied with GT, right? So this is just rho is basically replaced with rho 2 and 1 minus rho 2. Then these bias corrections for both, and then the weight update is same as the RMS prop. So if you go ahead with this Adam algorithm, this is the full algorithm, but I think I have described the components. I will just give you time to basically read it at your own leisure. The last slide is this visualization. So I have taken this from this link. You can have a look at this link. This has a simple description of different other strategies also. But when this blog was written, actually Adam was not there. So this Adam, but it works best till now. I mean, there are other modifications of Adam that has come, but yeah, I mean, as you said, things are going fast, so I will not have time to cover all those, and it's not required. I mean, for the purpose of an introductory level deep learning course, that is fine. So you see that SGD is this red one, and it's still moving. I mean, it's not a very well behaved loss function. I mean, it's an elongated one, so that's why that effect is more pronounced. It's jittery. The one that is actually working good is this ADA-grad, these blue ones. For this green, that is this, and instead of accelerated gradient, they are actually overshooting and coming and so on. So these problems are there. So this is the, I think, the last slide that I had. Now I will go back to this slide, and yeah, Anupam, you had some questions. I will ask you to unmute.
Sir, my question was, sir, with I know that one of the big problems with learning is the idea of minimize or like what's it called? I forget. 1 second, sir. It's called vanishing gradient problems, sir. Like the
vanishing gradient, yeah, vanishing gradient does not have anything to do with the optimization. It comes with when you basically stack lots of layers in case of RNNs, or rather a sequence when the input is a sequence, long sequence. So that we will come when we will discuss RNN. Okay. So
sir, but does it not apply in this case, because we are multiplying like 0.9 multiple times?
Yeah, vanishing gradient, this term is used in a different context. So okay, if you mean that in RMS prop, okay, I am dividing it always with some positive value, or not RMS prop, that ADA-grad, that yes, is taken care of by this RMS prop. So you are exponentially averaging. So you are giving only importance to the few recent ones. So you can do that moving window also, that ADA delta. So for thinking about that, okay, I will not take, if I am the 1000th iteration, I will not take all the values squares, gradient value squares from 0 to 995. I'll just take from 996 to 1000.
The first few ones.
Yeah, just the few ones. That is the moving window one. But that is not the vanishing gradient problem. It's completely different, right?
Okay.
Okay.
So my question was, sir, like if it does it decrease how much we're learning, because we keep like the steps that we are taking is getting reduced by a certain variable all the time?
Yes, you can see. I mean, it stalls the learning. I mean, the ADA grad one. That's why this correction has been employed, right? So if you don't employ the correction, that is the RMS prop, then yeah, I mean, you might get stuck if you are starting with very far away from the minima. Your initial theta is very far away. Maybe after a few iterations, 1,000 iterations, it is stuck somewhere, and the learning rate is, I mean, the step size is so small that it is not moving at all, sort of. But then comes the the expertise of the practitioners and so on. He might just try to increase the value of epsilon. He might just try to use the other one, say RMS prop or the ADA delta. Yes, so of course ADA grad stalls the I would say learning, stalls the learning, not the learning performance, but that stalls the learning, and that was the reason, right? Okay, I see Sayan has some question. I'm just asking you to unmute. Yes.
So these variants of gradient descent, do they have any protection in cases where like the loss function has multiple minimas?
No.
Like
no. So
okay.
multiple same minima, you are saying, right? I mean, all the minimas are same value. That is, the J theta values are same for all the minima, or
no, not like
okay.
There's not global minima, but many local minimas.
I mean, there is always a global minima, but many multiple local minima that you are saying, right?
Yes.
Yeah, no.
So what if it goes stuck and in one local minima?
There is no such guarantees. But yeah, deep learning actually circumvents this problem. That's why I asked you the question, like whether all the local minimas give the same value, because deep learning, it has been shown. I think the person's name I am forgetting. Probably it is Misa Belkin. So they do a lot of research in this domain, and they have shown that, I mean, your surface of loss that is in deep learning, I mean, when you have lots of these compositions of functions, there is compositions of these different layers and so on, generally the loss surface close to the minima becomes flat. So even if there are multiple minimas, they have the same value. So if you find one theta corresponding to one minima and another theta corresponding to another, somebody else finds another theta corresponding to another minima, if the minimas are same, that is the J theta values are same, you are doing equally good. So that is again a very high level overview of it. I mean, this goes very deep into theory of deep learning, so which we don't have scope to actually, and I don't know much of
okay.
Right.
Okay.
Yeah. Any other questions from anybody? You please raise your hand then if you have any questions. Okay. If not, then yeah, I will stop it here. And next week, yeah, we are lagging one lecture, but yeah, I will change the schedule accordingly. And yeah, one thing is that Tuesday there will be office time at 6. Yes. So if you have any questions on like anything that has been covered, please come. The link will remain the same, right? Okay. Yeah, I'll leave you with this then. Thanks a lot.